Good morning, everybody. So we're going to start the first part of a session that is divided in three. This morning it's mostly focused on geochemistry, and then this afternoon we have two sessions basically divided according to disciplines. It's in a different room, it's upstairs. So mantle plumes, what do we really know? Before we move on, for all the speakers, the light will turn orange at 12 minutes and red at 14. There's only one microphone, and that's about all you need to know. So our first speaker today is Alof Mann, and he's going to talk about composition of Hawaiian double-track volcanoes, shallow or deep controls.
Good morning. I should start by saying that this talk should really be given by Cinzia Farnetani, since she's done most of the work that I will present here. But she couldn't come, had to stay home because her husband came to San Francisco. Anyway, what I want to address is an issue that's both old and new. It's old, that it's been known for a long time that the Hawaiian volcanoes really were two lines of volcanoes. They were known as the lower track and the Kea track, and you see them here in blue and in red. Just how different they are in composition became very clear with the work of Wafa Abushami in 2005, and you see that the blue volcanoes here have isotopic compositions which are essentially completely separate from those of the red volcanoes that are from the Kea trend. And there has been some kind of debate raging over what that means, whether this signal comes from deep or whether it's generated in the uppermost part of a locally heterogeneous plume. So what does this mean? Meanwhile, just in the last year or so, people have looked elsewhere for this phenomenon and found it. Here are three island groups in a paper by Huang et al. In Samoa, well, the Marquesas, the third one will appear in a minute, that also have more than one track of volcanoes and also different isotopic compositions. Here you see the Samoa situation in comparison to the Hawaii situation, where these two, the southern and the northern trend, the Vai trend, has the blue isotopic compositions, and the Malu trend has the green compositions, just like this laser pointer. And so, and it goes on from there. The Marquesas paper just published this year by Catherine Chauvel and others, a similar kind of situation. These two tracks here, again marked in different colors, parallel, have different isotopic compositions. I'm not going to explain to you what all these isotopes are. I suspect that 99% of you who know what they are, and the rest of them think of them as colors. Okay, so it's good enough. Okay, so then yet another one is just being published from the Society Islands by Payne et al. In geology. Again, two tracks, and again somewhat overlapping, but nevertheless statistically quite distinct isotopic compositions. And again, most recently, the same phenomenon has been found in the Atlantic. With the Tristan and Gough lines of volcanoes shown here in yellow and some kind of blue. Whoops. Where again they have different isotopic compositions. So it seems to be almost like a general phenomenon whenever a given hotspot produces two rather than one line of volcanoes, the compositions of these volcanoes are different from one another, and that's kind of strange because you think that the plume mixes things up and delivers sort of one signal to the surface. That's clearly not the case. So what is the origin of the isotopic difference between parallel volcanic chains? Basically you can classify all the models into shallow and deep, as you might guess. And I will give you one example of a paper of attributing this to shallow lithospheric or sublithospheric melting processes, or attributing this to large-scale heterogeneities in the deepest mantle where plumes presumably come from. So here is a paper by Balmer et al. That just came out last year in Nature Geoscience that had a very clever idea. They thought as the lithosphere here moves across the Hawaiian plume, it develops small-scale convective rolls which erode the bottom of the lithosphere and create some kind of a corrugated sheet metal effect that looks like this in profile. And when the plume impinges on that, when it hits up on top of one of these things, it undergoes higher degrees of melting than the part of the plume that hits at the bottom part of that. And if there are local heterogeneities distributed to that plume, they will then contribute different amounts to the final product. And they explain the difference between these two tracks by this effect. Now, being a geochemist, I thought this was actually a testable proposition. I have no argument with the physics of this model. It's a very elegant model. But with geochemistry, you can test of whether this is what's actually happening. One simple test is just a geochemical indicator of what the degrees of melting is something like lanthanum ytterbium, which varies roughly inversely with the melt fraction or the degree of melting. And also, if you have a mixed source consisting partly of pyridotite and partly of peroxenite, at a given melt fraction, the peroxenite-derived melts are expected to have higher lanthanum ytterbium ratios than the pyridotite-derived melts, because the peroxenites are some kind of enriched, presumably recycled ocean crust type material. And you can compare that with the actual observations on Hawaiian volcanoes. So in Balmer's model, they have the Keatrak volcanoes undergoing high degree of melting, which should sample more extensively the pyridotite fraction and should therefore produce low lanthanum ytterbium ratios. You look at the observations, the red Keatrak volcanoes have all the higher lanthanum ytterbium ratios, and vice versa. Looking at the lower track volcanoes in Balmer's model, you're looking at a thicker lithosphere with lower melt fractions, and there should be more preferential sample of the peroxenite fractions, which should produce high lanthanum ytterbium ratio, and the opposite is that. There's another quite independent test. So it fails this test. Of course, as a single volcano moves across the hotspot, it starts out with low melt fractions, namely in the Loihi stage. I'm not going to explain that, but it makes sense that when it starts getting into the melt region, that the initial melt fractions are low, and there are lots of alkali basalts, and they gradually become tholeiitic as the volcano moves into the shield stage, and the melt fraction then increases, and then toward the end of its useful life, the melt fractions decrease again. And so if the melt fraction affected the isotopic compositions, you should see that. And what I plot here is a parameter or two parameters related to lead isotopes. Again, I will not explain what these are. Think of them as blue and warm, cold and warm colors. And you can see that all of the lower track volcanoes have blue colors independent of whether they are from a low melt fraction like Loihi or high melt fraction like Mauna Loa, and the same thing is true for the Kea ones. So whatever effect may be caused by the local variation in melt fraction is completely overwhelmed by the effect actually caused, which must be from some other, essentially a source effect that is being transported up here. So I think this model, as elegant as it is, actually, maybe it'll work elsewhere, but it doesn't work for Hawaii. So this does not explain the bilateral volcano chemistry. And then Dominique Weiss had a neat idea, or something I always could have kicked myself of not having thought of it myself, because it's essentially in front of, in plain view. We all know about these low velocity anomalies in the lowermost mantle, and she simply drew attention to the fact that Hawaii, along a bunch of others, is coming from the edge of the northern edge of this feature here. And so maybe the lower thing draws from that side and the Ki thing draws from that side. And so we're sampling things from the deep mantle source. Now, so what Cinzia and Connie and I have done is to formalize that, greatly simplifies. We try to model the simplest conceivable case, essentially putting a north-south gradient in isotopic composition, again in colors, represented by colors going from blue via yellow to red, and as in the boundary layer from which the plume is drawn. And the conduit is sitting here right at the middle of this gradient in this first case, and we ask the question, what is the resulting plume conduit structure? Can this explain the nature of the Hawaiian plume, namely the double track type of plume chemistry? And maybe in more detail, can we actually predict the isotopic composition, the isotopic evolution of a single Hawaiian volcano as it moves across the hotspot and samples the plume? What you get is, when you draw this thing into a cylindrical conduct, is a strange kind of picture, which Cinzia has called a lobate conduit structure. Here are the lobes. And it has a couple of interesting and unexpected features. Namely, here you have a gradient where the extreme compositions are 2,000 kilometers apart. Sucking that into a conduit actually brings the extreme compositions in direct contact with one another in at the center of the conduit. Okay? And how that happens, you see when you simply consider one bar here and one bar there, just so you can see more easily what's actually happening. And we're going to look at the blue and the red bar. The red bar is located initially more closely to that, so there's going to be some kind of asymmetry, and we're going to watch this sort of a movie-like affair. And as it's being sucked into the conduit, which is going up here, the radius here is 500 kilometers, so it's a sizable chunk of core mantle boundary region. And there it goes. Now it's coming in here, and there it goes. And the lobe here in cross-section in that cylinder here starts looking like this, and you can see it happen there. And there it grows, and there it grows. Okay, and here are some additional details. The things that are from the base of that layer end up in the very center, no matter what. They end up in the center of the conduit, and this is the reason why the extreme compositions are directly juxtaposed in the center of the conduit. Okay, so now another test, you can say, well, this is something very special you've done, so why should that have any general significance? So what we did was we simply moved the conduit away from the center of the gradient, 500 kilometers to the north, and now, you know, on this first model that I just showed, the conduit is located here. Now we're moving in 500 kilometers to the north, and lo and behold, the thing looks a little asymmetrical, but you still have this basic feature, because ultimately all that stuff gets, even if it's a little farther away from the conduit initially, once you run that machine for a while, it all gets sucked into that conduit and gets juxtaposed at the center of the conduit. That's a very important feature. Okay? Now, the only case where you don't get a sort of a lobate structure is the cartoon we've all drawn before, namely that there's some kind of a perfect separation in the conduit, and you can have that if you have a sharp gradient, you know, a sharp jump in composition that's going right through the conduit. Again, if you move that sharp thing instead of a gradient away from the conduit, you start getting lobes again. So this is a very, very special case. You don't really expect this to happen, you know, in the real world very often, if ever at all. Now we want to watch what happens to this stuff when it moves up in the plume and gets sampled up at the plume head by the volcanoes. This is a fancy three-dimensional image of that. So the blue stuff is coming here. And on top of that, we have an actual slight angle between the orientation of this separation down here and the direction in which the lithosphere skates across the top of that plume head. So there's a 60-degree angle. And we'll watch what happens. And here you can see that angle, and the whole thing looks a little distorted. Here are the volcanoes, and we can now watch how a lower type volcano evolves isotopically as it moves from here to there. And you see the isotopic composition, the lead 208 to 06 ratio, first goes up and then goes down as you go from here to there. And a Kea type volcano just starts relatively high and then goes down. So potentially you can distinguish, you can actually map these well. We can compare this with actual observations, not very well because we only have one volcano. Am I already out? Yeah. Okay, then I'll stop here. You can watch Mauna Kea seeing early on doing this and then decreasing in 208 to 06 ratio as you go along. The other volcanoes, you can see it in some of them, but we don't have the kind of stratigraphic information that would make that good. I will skip over the other things here and just come to the conclusions. So the geochemical zonation observed at Hawaii and at other hotspots reflects large-scale heterogeneities in the deep mantle. A large gradient of lead composition generates a slow-bait zonation in the conduit and distinct isotopic composition between Kea and lower volcanoes. The low-bait plume zonation is independent of the initial distance between the conduit and the isotopic gradient. Thank you.
Thank you, Al. Questions? Yes.
Yes, these were the slides I skipped. If the angle is 90 degrees, you see nothing, okay? Each volcano moves from one to the other. If the angle is 45 degrees, you still see it. The initial model was 63 degrees. But up to 45 degrees, the feature is well preserved. Only when you go close to zero, then you don't see it anymore.
I have another comment about this, and that it appears that you're using a uniform viscosity. Some properties of things that you see at the bottom of the lower mantle have possibly L associated with them, or at least low seismic velocities, in which case you have different viscosities. And this perfectly symmetric flow-based structure would be destroyed by that.
Well, this is an assertion you are making, first of all, that if you have a different viscosity structure. We took the attitude is when we look at this thing, we should look at the simplest case first, okay? Purely thermal convection. We are going to work on thermochemical type of convection with density differences and viscosity differences next.
I suggest we continue that discussion this afternoon. Next speaker is Mike Garcia, who is going to talk about the age, geochemistry, and melt flux variation along the northwest Hawaiian Ridge.
Thank you, Dominic. Welcome all. I'd like to share with you some of the work we've initiated on the Hawaiian Northwest chain. This is a group effort. I'm here representing people from many different institutions. So if we can move to the first slide. Al has already introduced you to the Hawaiian Islands. I don't think I need to say any more about them. But what I would like to address is what's beyond the Hawaiian Islands and what we know about them. And what I want to emphasize is not much. So here's a map of the North Central Pacific, and you can see the Mid-Pacific Mountains in the south, the Aleutians in the north. We're looking at the area between... We're looking at the area between the Hawaiian Islands down here and the bend where the emperors come down. So we're looking at this northwest Hawaiian Ridge. Okay, so we're going to talk about four facets of the geology in this area. what's known about the surveying, what's known about the geochemistry, what's poorly known about the geochronology, and also a problem that has been addressed many times over the years, but still not been resolved in terms of the change in flux of magma along the chain. So today we'll be updating you with some new information on bathymetry as well as some whole rock XRF data, and I'll be giving you more questions than answers. Okay, first of all, the Northwest Hawaiian Ridge, where is it in detail? So from the Hawaiian Islands, which stop here with Ni'ihau, the first seamount in the group is Middle Bank, and we extend up to the Bend. You can see some familiar names, Abbott and Colohan. So this part of the chain, and what John has done, John's compiled all the bathymetry, is tried to address what are the seamounts. And so we've taken a conservative perspective here in terms of considering only things that lie along the axis of the Hawaiian chain. The North Central Pacific is full of old Cretaceous seamounts, and these have been dredged on several occasions, so they add a complication in terms of identifying what is and is not part of the Hawaiian chain. So we've taken a conservative approach and said, well, we're going to look at things that are along the chain, along the axis of the chain, and things that have been sampled that we know are young and part of the Hawaiian system. So what you see when you do that is there are tremendous variations in the size and shape of these volcanoes, from tiny little volcanoes less than 1,000 cubic kilometers, at least on a Hawaiian scale they're tiny, to things that are approaching the size of Mauna Loa, which is down here, and that's Garner Seamount here. The shapes of them show dramatic variations as well. There's some really bizarre shapes in the Hawaiian chain, and John hopefully will be getting a paper out soon on that. The shapes of the chain, the volcanoes are obscured by coral platforms that have developed on top of these things, and so there may be multiple shields hiding underneath the coral platforms. Until we get some more gravity data to define them, we won't know for sure. Okay, so this is a movie. I hope it's going to work. Ooh. Okay, so this is a flyby that John put together to give you a perspective of what the Northwest Hawaiian chain looks like. So we're zooming in here on the south end of the Big Island, and we're going to fly up the chain. I wish I could speed it up. But anyway, here we are going down the Hawaiian Islands, and here's the first volcano, Middle Bank, and we're proceeding along. Here's Garner Seamount. Look at some of the shapes of these things, very elongate rift zones, and multiple coral platforms. Here's Morrow. Northampton, a very elongate ridge. The Midway area here, there's multiple seamounts. How many of these things are actually part of the Hawaiian chain? We're not sure because most of them have not been sampled. Okay, we're now approaching the bend, and notice the sparsity of volcanoes. This is an area where the productivity has dropped off dramatically, and here we're getting up to the bend in the chain, and this is the southernmost seamount in the Hawaiian group. Now, one thing I want to draw your attention to, one of the good things Bush did was he declared a marine sanctuary, the largest sanctuary on Earth, and unfortunately this means this area is virtually closed to sampling. So we're working on samples that are in collections, both the University of Hawaii and Scripps, and we've sampled 12 volcanoes from these collections. So this map shows you where we have samples either we've worked on or have been worked on by Clegg and others. And so far, we've counted 25 volcanoes that have been sampled. 3 are new samples, new sites we've been sampling. And so less than half of the known volcanoes have been sampled. And most of the sampling has been done by a single dredge haul. You lower a bucket, you drag up the side, and in many cases there was a very limited variation within these buckets. But what we found is 12 of them have shield stage thallitic volcanism, and 12 have alkalic lavas that we think are part of the post-shield stage, and 4 have what's been identified as rejuvenated volcanism. Okay, so how do you do that? Well, this is a nice diagram that is based on the work of Gordon MacDonald, where he was able to divide Hawaiian volcanoes into a shield stage and a post-shield stage. And you can see here we have a number of new samples from the shield stage, thallitic volcanism, and then the wide variation we see in the post-shield stage. from typical basalts or basanites up through trachytes. So quite a range in composition. If we look at an MGO plot, we see a lot of the samples have high MGO, particularly the islands. There are several eroded remnants of islands, very high in MGO. And like typical Hawaiian rocks, the fractionation scheme is dominated by olivine and then by clinopyroxene. In the very late stages, the titanium goes down, so they've experienced some titanium fractionation. What is surprising, as Matt Jackson and others have said in the past, is the nice linear trend for Hawaiian lavas. What is also surprising is the lack of rejuvenated volcanism in the samples that we've looked at. In the Hawaiian Islands, about 50% of the volcanoes have second stage secondary volcanism, and so far only 4 volcanoes have been reported from this sequence out of 52 with secondary volcanism. So we're wondering why are we missing these things? Because they should be the surface. They should be mantling these volcanoes. They should be the easy things we pluck as we sample. And we think it's perhaps either due to they've covered by sediment, the corals, or maybe they never formed. So here's a map showing the locations of identified rejuvenated volcanoes. You see that they're distributed all along the chain. This area here in the northern Hawaiian Islands has prolific amounts of secondary volcanism. This was shown by Dave Clegg and by a cruise that Dominique and I were out on. There's extensive secondary volcanism here, but beyond that, it seems to be relatively sparse. All right, here's a compilation that Dominique and her student Lauren put together, Lauren Harrison, for what's known about the isotopic variation in the Hawaiian chain, and emphasize 2 things. The emperors are relatively well known. This story has been developed showing that the strontium isotopes increase with time. And this is some very old work that was done by Marv Landfair and others in the central part of the Hawaiian emperor chain. And none of these samples were done by stepwise leaching. So we're not sure how good these data are. Another thing to point out is the neodymium isotope, which should be less sensitive to alteration. And you can see that there's maybe a slight decrease in trend along the chain. But what is also interesting is the relatively depleted compositions that were identified in the emperors seem to persist along the Hawaiian chain. So this depleted component, which Fred Fry identified in the emperors, seems to persist along the chain if indeed these things are not too heavily altered. Okay, what is surprising is the dearth of lead data in the central part of the chain. There is no modern work in the central part of the chain. What is also interesting is there are 2 samples from the northernmost part of the Hawaiian chain that seem to have lower-like compositions. So it's going to be exciting to fill in this gap and find out what's been going on and when did this lower component materialize in the Hawaiian chain. Here's also a plot of strontium versus lead isotopes, the East Pacific rise field, the emperor trend, and then again the Kea and lower trends, and then this northernmost northwest Hawaiian Ridge volcano that seems to plot in the Mauna Loa field. So it'll be interesting to see what the other samples in this train are doing. Okay, the ages. We've all come to believe that the Hawaiian chain is well characterized, and indeed I'd argue that that's not the case. This shows the distribution of ages and the types of ages. And what's important to notice that only 16 of the volcanoes in the chain have been dated. 10 of these were tholeitic, shield stage. Most of the rest were younger volcanoes. And only 4 of the volcanoes have been dated by modern geochronology. So the kind of work that Bob Duncan and others does has only been done for 4 of the volcanoes here. And when that work was done, it increased the ages dramatically. In comparison, Louisville Ridge has now become the gold standard for oceanic island groups. It's well studied, well characterized, and in contrast, the Hawaiian chain is poorly understood. So here are some of these samples that were redated by the modern argon. You can see the dramatic increase in ages for those samples. So it's uncertain what this distribution is telling us. Yes, there's an overall increase in age, but you can see there's a great deal of scatter. So depending on how you want to look at that, there are sections of the chain that have essentially the same age over a 900-kilometer distance. What's going on? Another interesting problem is what is the age of the bend? Recent papers said it was around 50 million years and correlated with activity, the initiation of activity in the Western Pacific, the island arcs. But depending on how you look at this data, you might put that age somewhat younger, perhaps around 48 to 49 million years. And if so, the bend is not synchronous with the Western Pacific island arc volcanism. So we're hoping to do more work in geochronology to better sort out what the age of the bend is. Okay, I mentioned earlier about the change in flux along the chain. There's been a long history of work looking at the variation in volume along the Hawaiian chain. So here we're up in the northernmost emperors going towards the Hawaiian Islands. And depending on whose study you look at, you can see there's quite a bit of variation, but there's some consistent themes. And one is that the emperor seamounts have relatively low output and sort of moderate to low variations. And another striking thing is that the decrease in output doesn't come at the bend, it's after the bend. So the volcanism didn't drop off right at the bend, it dropped off after the bend. But following the bend, volcanism has dramatically increased. And so you would ask the question, why? What's going on there? Well, there's several different potential causes for this. One is plate thicknesses. You change the plate thickness, you might see a variation. White looked at this and said, no, that's not what's going on. Perhaps you could address this by changes in plate stress, reconfigurations. That's a possibility that my colleague Paul Wassel is going to be looking at over the next year. Another is to relate it to somehow the plume has been drifting, but the plume stopped drifting about at the bend. So as far as you know, since the bend, the plume has not been drifting, so that's not likely to be a cause. One is a change in the melting conditions. Either you had higher temperatures or lower pressures allowing more volcanism. That's something we will be assessing. And the other aspect is changing the source composition, either in the rock type, getting more peroxenite rather than peridotite, or that you've changed the fertility of the source. You're dealing with a source that's more fertile, so you're producing more volcanism. So our goal over the next year is to evaluate some of these variables. So in summary, in terms of this theme of this session, there's a lot we don't know about the Northwest Hawaiian Ridge, and we hope next year we'll be able to update you on what's going on. The bathymetry is still not well characterized. There are dramatic holes in our knowledge of the Northwest Hawaiian Ridge. We hope to be able to assess that more with new work. We're going to do a lot of new geochronology work. Hopefully we're going to look at 20 different volcanoes, multiple samples. We're doing lots more of XRF work as well to assess, and probe work to assess the variations in rock types to see if that's the cause of what's been causing the change in volume in the Hawaiian Ridge. And then Dominique and others will be doing this isotopic study to assess whether the components in the Hawaiian plume have been changing. I want to thank two people who have been instrumental in the work presented today, Alex Haskethurf at Scripps for finding samples from the Scripps collection and sending to us, and Mike Vollinger at UMass for doing XRF analyses. Thanks very much.
Thank you, Mike. Questions? Yes, Kash.
Yes, that's certainly possible. And hopefully we'll assess that doing the isotopic and trace element work. So that would be the obvious explanation.
We need to move to the next talk, which is by Aaron Petrushka. It's the second invited talk in this morning. Aaron is going to talk about the origin and chemical heterogeneity in the Hawaiian Mantle Plume.
Okay. Good morning, everyone. So I'm going to zoom in with this talk and focus on the three active Hawaiian volcanoes, of course, Kilauea, Mauna Loa, and Loihi Seamount off the coast of the Big Island. The reason I'd like to focus on these volcanoes is because we think they overlie the most actively upwelling portion of the Hawaiian plume. So by looking at the chemical and isotopic variations of the lavas from these volcanoes, we can get a nice snapshot of the current distribution and origin of heterogeneities in the plume. Al gave a great introduction to some of these background ideas, so I'll just talk about them very briefly. Hawaiian lavas, volcanoes seem to lie along two geographic trends, the Kea trend, which includes Kilauea volcano, which I'll talk about, and the Loa trend, including both Mauna Loa and Loihi seamount. So many studies over a long period of time have identified very distinctive chemical differences between lavas, isotopic differences between lavas from these Hawaiian volcanoes. And one recent important interpretation is the idea that this is related to some kind of bilateral asymmetry in the Hawaiian plume represented by the different colors for the Kea trend and the Loa trend side. And that's mostly based on high-precision lead isotopes. And I think most of us agree that these chemical and isotopic differences are sourced from deep mantle heterogeneities within the Hawaiian plume, but there's less agreement in terms of their origin. And so one sort of idea you hear frequently is that the Loa side is related to some sort of enriched material, whereas the Kea side is related to some sort of depleted material. Here's the isotopic evidence for these differences, which you've seen earlier, focusing on just the three active volcanoes, the lead-lead isotopic diagram. The dashed line is the Kea Loa line from Abu Chami et al. Of course, Loihi and Mauna Loa plot above the line with higher 208, 204, and Kilauea, a Kea trend volcano, plots below the line. And what's been pointed out even more recently by Dominique is that over 96% of analyzed Hawaiian lavas going back about 5 million years seem to follow this basic pattern on the lead-lead diagram. And here again is Dominique's explanation for this, where you have perhaps some sort of enriched material that might be recycled oceanic crust, preferentially incorporated on the Loa side of the Hawaiian plume, whereas perhaps the Kea side of the plume is preferentially tapping some sort of ambient Pacific lower mantle, depleted material. I'm going to take a different approach, step away from the lead isotopes today, and focus on the incompatible trace element abundances of Hawaiian lavas to try to get at some of these questions from a different viewpoint, and specifically propose a quantitative mantle source melting model for the active Hawaiian volcanoes. In order to do this in a sort of good way, I think it's important to add one additional volcano that's not an active volcano, Ko'olau. Ko'olau is important for a variety of reasons. It's here on the island of Oahu. It's thought to lie along the extension of the Loa trend. But it's really important because it erupted lavas that have extreme Loa-type compositions. You can see this most clearly on this lead-lead diagram. Again, Ko'olau lavas have relatively low 206, 204 lead isotope ratios with elevated 208, 204 at a given 206, 204. So it's a really important compositional end member. Okay, so this figure shows the data I'll be using for pretty much the rest of the talk. This is a range of literature data and some new data. The top plot shows primitive mantle normalized trace element patterns for Kilauea volcano as a representative of the Kea trend. Each of these symbols are different lavas from Kilauea volcano. And on the bottom are the Loa trend, geographic trend volcanoes, Loihi in blue, Ko'olau in the darker color, and Mauna Loa in the light brown. And so the basic trace element patterns that you see here have been excuse me, I should say that these patterns are actually estimated parental magma compositions. I took average lava compositions and normalized them to high magnesium by equilibrium olivine addition. And so the basic trace element patterns you see here have been well understood for many, many years based on the work of Al Hoffman. So you see a wide range in the abundances of the highly incompatible elements due primarily to variations in the degree of partial melting. In contrast, you see relatively constant and low abundances of the heavy rare earth elements, and that's due to the presence of residual garnet in the source. In contrast, there are a number of enigmatic features of the trace element patterns, especially for the highly incompatible elements that are not as well understood. I'm going to focus on two. One important feature are these thorium depletions that seem to be a ubiquitous feature of Hawaiian tholeiitic shield lavas. So they're both for Kea and Loa trend volcanoes, you see low abundances of thorium and uranium as well, relative to rubidium, barium, niobium, and the light rare earth elements. And so Hoffman and Yoakum proposed that these thorium depletions were a signature of plagioclase-rich recycled oceanic gabbros. The second anomalous feature we see in the trace element patterns are these positive niobium anomalies. Now these are volcano-specific, so you see positive niobium anomalies at Kilauea volcano, especially in the more enriched samples, and you also see even larger positive niobium anomalies at Loihi seamount, a Loa trend volcano. But you don't see them at Ko'olau and only a slight amount at Mauna Loa. Okay, so the framework I'm going to be working within is the idea of that the Hawaiian plume contains recycled oceanic crust. Specifically, there are fragments of variably altered and dehydrated mid-ocean ridge basalt and oceanic gabbro in a matrix of depleted mantle. Okay, so let's just talk qualitatively where I think thorium depletions come from. This is the trace element pattern for average mid-ocean ridge basalts, and you see they have low thorium abundances relative to niobium and the light rare earth elements, and this is a simple consequence of the fact that this is a pattern that's depleted in incompatible elements. However, if you look at the chemistry of altered oceanic crust drilled from the seafloor, that's this light-colored range of patterns for a variety of drill holes. You see that altered morb due to interaction with seawater or hydrothermal fluids have enrichments in rubidium, barium, sometimes uranium relative to thorium. And you also see this kind of pattern in lower crustal gabbros drilled from the seafloor, again, enrichments in these elements compared to thorium. So the idea is that if these sort of signatures can somehow at least partially survive the process of subduction and dehydration and then be reincorporated into the Hawaiian plume, Hawaiian lavas would have thorium depletions relative to some of these surrounding elements. Okay, what about the origin of the positive niobium anomalies? We see this again at Kilauea and at Loihi Seamount. You can't explain positive niobium anomalies simply by melting some sort of depleted source, whether it's recycled mid-ocean ridge basalt or depleted mantle. You need to have some other process or component. And many studies have noticed that ocean island basalts have positive niobium anomalies, and one of the traditional interpretations is that these come from dehydration of the recycled oceanic crust during subduction, probably in the presence of residual rutile, and that ends up creating a residual slab that's enriched in niobium and other high field strength elements, and we think that's what's important for these Hawaiian lavas as well. Okay, so what I want to do finally is put this into a more quantitative context. So we made a simple mass balance model that takes into account 3 different source components. There is an altered mid-ocean ridge basalt represented by fresh morb that allows for enrichments in rubidium, barium, uranium, and a slight enrichment in strontium. We assume that the source contains fresh recycled oceanic gabbro represented by the yellow symbols, which has a positive, for example, strontium anomaly due to the fact that it's accumulated plagioclase. And then some sort of ambient Hawaiian mantle that has a slightly depleted pattern here. The model assumes that the altered mid-ocean ridge basalt can be modified by dehydration during subduction according to the mobility of the various trace elements in fluids based on experimental studies. The model allows for variations in the degree of melting. And then finally, we test 2 different scenarios for source lithologies. In one case, we tested the possibility of a homogeneous peridotite source based on the thinking of Putirka. And then we tested the idea of Sobolev that the source may contain a mixture of peridotite and eclogite that react to make secondary peroxenite. And I should just say the model works equally well in both cases. So here are the results for Loihi Seamount. Loihi turns out to be a model N member. The model works best with a gabbro-free source that has about 8 to 11% recycled altered morb. If you look at the model results without any dehydration of the recycled morb, you get a very poor model fit for the highly incompatible elements. However, if you allow for about 11 to 13% loss of fluid during subduction, you get a dramatic improvement in the overall model fit with positive niobium anomalies and thorium depletions. So the other end member for the model is Ko'olau, and the Ko'olau model results suggest that Ko'olau has about 8 to 10% altered mid-ocean ridge basalt and 7 to 8% lower crustal gabbro. You need the lower crustal gabbro to explain the positive strontium anomaly, 40% anomaly you see on average at Ko'olau. So unlike Loihi, the model works pretty well without any dehydration of the subducted material for Ko'olau. You get a pretty nice model fit. There's a very slight improvement in the residuals if you allow for about 0.2 of a weight % fluid loss at Ko'olau, but it's really minimal. Okay, I want to summarize up the model results for the 3 active volcanoes here: Loihi, Kilauea, Mauna Loa, and then of course Ko'olau off to the right here. This figure represents just sort of a map view of what we think of as the distribution of heterogeneities in the Hawaiian plume based on these results. The first thing I wanted to mention is that it appears that there's a significant amount of recycled oceanic crust in the source of all 4 of these Hawaiian volcanoes based on the trace element model results. And so this, it ranges from something about 10% as much to almost 20%. So that suggests that the differences we see between Kea and lower trend volcanoes is not related just to the presence or absence of enriched versus depleted materials. There's enriched materials, i.e. recycled oceanic crust, in all of these volcanoes sources. In more detail, you see that it appears that the total amount of oceanic crust increases from Loihi to the southeast. To the northwest, it goes up a little more, and then the greatest amounts today at Mauna Loa and slightly higher at Ko'olau. So there appears to be a gradient. There also appears to be a gradient in the amount of recycled oceanic gabbro based on the model results from none at Loihi and increasing amounts as you move towards Kilauea and Mauna Loa, with Ko'olau having the greatest. In contrast, the model results suggest that the extent of dehydration for the altered morb decreases as you go from Loihi in the southeast toward the north to the northwest. So taken together, these model results suggest that there is actually a northwest, southeast-oriented gradient of small-scale heterogeneities in the Hawaiian plume that are related to each other by differences in the amount and type of recycled oceanic crust and the extent to which it was processed during subduction. So bringing these sort of model results all together, we think that it suggests that there's a relatively complete package of recycled oceanic crust in the Hawaiian plume without sediment. Sediment is not required for the model. This recycled oceanic crust has probably been variably altered prior to subduction, and then it was dehydrated during subduction. And then different Hawaiian volcanoes sample different portions of this residual slab that correspond to differences in the original depth of the oceanic crust. So the model results suggest that Loihi and historical Kilauea lavas have a lot of similarities. They both sample gabbro-free and strongly dehydrated material that probably corresponded to the uppermost portion of the residual slab. In contrast, Ko'olau and Mauna Loa, I would group together. The model results suggest they have a gabbro-rich source with a weakly dehydrated mid-ocean ridge basalt component that probably corresponded to the lowermost portion of the original residual slab. Okay, so I just wanted to mention a few thoughts about the lead isotopic variations and how they might relate to this kind of thinking based on the trace elements. Experimental studies and observations of volcanoes suggest that the mobility of lead in fluids is much greater than thorium and uranium. So if you have a mid-ocean ridge basalt crust that's strongly dehydrated during subduction, it will tend to end up with high thorium lead and uranium lead ratios, and over time they would develop very radiogenic lead isotope ratios. This is the classic explanation for high mu-type signatures by many studies. So in terms of the model results, if Loihi and historical Kilauea lavas have a source within them that has been strongly dehydrated in an ancient subduction zone, they would end up evolving to high lead isotope ratios, and that's what we see for both Loihi and Kilauea. In contrast, the model results based on the trace elements suggest that Ko'olau and Mauna Loa lavas have a weakly dehydrated recycled source, which over time would develop to low lead isotope ratios, just like we see for these volcanoes. Thank you.
Time for questions. Yes?
That's a possibility.
Yes?
Hi.
I just find it odd that you're talking about dehydration of the source region without actually including all the volatile work that's been done on the Hawaiian plume. So I suggest you incorporate that into your work and
Okay.
inconsistent with your focus.
Okay.
If there's no more question, we'll catch up time. And we'll move to the next talk, which is by Matt Jackson. And Matt will talk about major element variation in Hawaiian shield lava, source features, and perspective from global OIB systematics.
Morning, everybody. I'm a shameless promoter of Mantle Plumes. I see Mantle Plumes every day. In fact, I cross the street and go to Starbucks. I find that about every 10th batch of the conveniently called marble cake at Starbucks, it gives you a nice plume. My colleague, Paul Hall, a dynamicist, very much appreciates this in at many levels. So this is an important year. It's a 30-year anniversary for an important hypothesis, the hypothesis of deep recycling. And I'm actually, many of you have probably seen me put up this slide before, so it's convenient that I'm recycling a slide about recycling. Al Hoffman and Bill White had a couple of important papers in 1982 that suggested that the major element or the isotopic heterogeneity that we see in the mantle sampled by hotspots can be explained by subduction of ancient oceanic crust, ancient sediment that are sent into the mantle and brought up again in mantle plumes. And I think this is a great hypothesis, and people have been working on testing this hypothesis for the last 3 decades. Just very simply put, oceanic plates, both crust and sediment, enter the mantle at subduction zones. So here's a nice figure from Rhea Workman's paper in G cubed showing a plate forming at a ridge with a thin veneer of sediment covering the basaltic layer. This package goes into the mantle at a subduction zone. The big question is what happens to this plate over geologic time. The plate is thought to enter the mantle and reside in the deep mantle for some unknown period of time and perhaps rise lava lamp style and partially melt near the surface where the lavas erupted at Ocean Island basalts. So we look at the chemistry of Ocean Island basalts sampled by, fed by mantle plumes to evaluate the hypothesis that these ocean island basalts are being fed by deeply recycled material. So let's turn to the Hawaiian hotspot. It's the archetypal plume-fed hotspot that's often just recently by Aaron, but traditionally suggested to be fed by deeply recycled materials. So major element heterogeneity should accumulate in a mantle over geologic time as you subduct oceanic plates. Both the mafic lithologies and the sediments, these should be very different or are very different from the peridotite lithologies that dominate the mantle. So over geologic time you should see variations in major elements accumulate in the mantle, and mantle plumes erupted beneath or sampled beneath hotspots should be, the lava should then reflect this heterogeneity in major elements. And in 1996, Eric Howery had a very important paper showing that actually the neodymium isotope compositions of Hawaiian hotspot lavas relate to the major element compositions of those lavas. And this is very important because neodymium isotopes reflect the mantle source that's contributing to these lavas, and the correlation then with major elements suggests that at least a part of this major element variability must also reflect the mantle source variability beneath Hawaii. And with my colleagues, Dominique Weiss and Shixin Huang, we turned to the GeoRock database to look at what's happened to this particular trend with 17 years of additional data. We looked at shield stage lavas only. We excluded the most evolved lavas and the most altered lavas, and we corrected for olivine fractionation in addition to a constant MgO of 16 weight percent, which, by the way, gives you average lava compositions that are in equilibrium with Forsterite 90 or very, very close to it. And you can see that overall this trend is very nicely holds. It's interesting to note that you no longer really need to average the volcano compositions to see a trend. You can look at individual data just to show how we're dividing this up. The warm colors are Kia trend volcanoes, and the Loa trend volcanoes are blue colors, and they separate quite nicely. In many cases, I start to ask myself, well, maybe this is putting the isotope geochemists like myself out of business. The major elements that show such striking positive correlations with lead isotopes. You you can see in this particular case the three traditional Hawaiian components resolved quite nicely: Ko'olau, Kea, and Loihi. It's interesting that this particular Loihi trend right here also includes high helium 3-4 lavas from other volcanoes. Mahukona also plots in here, for example. The highest helium 3-4 lavas from the HSDP trend plot right here as well, whereas the lower helium 3-4 lavas from the HSDP trend plot down here. So it's very nice to see these trends that Eric first observed to be reflected in the additional data, and that you can now resolve this by looking at individual data points. But the bigger issue for me here is what Hawaii really represents in the global scheme of things. So here's the Hawaiian data again, silica versus lead isotopes. And what I've done is I've plotted these data here. It's just a nice inset. And I've included the work that I did with Raj Dasgupta showing the global ocean island basalt database. And you can see that the Hawaiian database really is a microcosm for the global ocean island database, whereas the Ko'olau lavas anchor the high SiO2 unradiogenic lead component here, and the really radiogenic lead isotopes and very low silica compositions are sampled by more high mu volcanoes, sampled by Mangaia, Tubuai, St. Helena, and so forth. What's really neat is that these lower silica Hawaiian lavas are trending up towards this high mu component, and really Hawaii is very much a microcosm of the global array. And I think that processes that generate major element variability in Hawaii are the same processes that are driving major element variability in OIB, in the OIB mantle sources in general. So going back to Aaron Pertuska's talk, a very nice summary of how we think this is going on. I think it's driven by subduction zone processes, ancient subduction zones, where you have variable silica and extraction from slabs. The slabs that have suffered the most silica extraction, dehydration, end up providing you with silica undersaturated sources. These sources also suffer more lead depletion in the subduction zone, as Aaron alluded to, but the thorium and uranium is not as severely depleted in the slab. So you have high uranium-lead ratios and low silica contents here. So the big question here for me is, okay, do we really know that this material is recycled crust? Do we know that it was once at the surface at some point in geologic history and has gone down to the mantle and come back up again? So at this point, I'm going to suggest a way to test the hypothesis. This is work that that my student has done. If Rita Cabral is here, raise your hand so people can talk to you about this. Rita's in the back. And together with some collaborators, Ken Estelle Koga, Martin Whitehouse, Michael Antonelli, the two Jameses, Farquhar and Day, and Eric Howery. So we've realized that you get very unusual sulfur isotope fractionations, mass-independent sulfur isotope fractionations before 2.5 billion years ago. And after 2.5 billion years, you realize that this cap delta 33S, which represents the degree to which the sulfur 33 has suffered mass-independent fractionation, you notice that this really has shut down after 2.5 billion years. So wouldn't it be neat then if you could find these mass-independent sulfur isotope signatures in ocean island basalts? Because that would really be a timestamp and a certificate, as Norman Sleep says, that this material is once at the surface, and it would tell you when that material was at the surface. So here's just an illustration of how mass-independent fractionation is quantified. Delta 34S on this axis, delta 33X on this axis, and all data on terrestrial samples should fall on the mass-dependent fractionation line, at least all samples from 2.5 billion years. to the present day. And Archean samples can plot above and below this line. The degree to which they plot above or below that line tells you whether or not you have enrichment in 33S or depletion in 33S, driven by a mechanism that is not a function of the different mass, the mass differential between 32, 33, and 34S. And James Farquhar in 2000 suggested that the cap 33S anomaly, as you see in the Archean, but not after 2.5 billion years, owes to atmospheric photochemistry involving sulfur dioxide, other sulfur species coming out of volcanoes in a primitive atmosphere, where you have an atmosphere that has less oxygen, therefore it has less O3, and so the atmosphere is transparent to ultraviolet radiation. Ultraviolet radiation, high energy ultraviolet radiation, is responsible for fractionating the sulfur into reduced and oxidized species that have either enrichments or depletions in 33 sulfur that has nothing to do with the mass of the element. So here's a nice cartoon that Rita put together that shows the deep sulfur cycle before 2.5 billion years ago. You have a number of sulfur species in the atmosphere that react with UV radiation. You have both reduced species and oxidized species. The reduced species, as a result of this photochemical reaction, have enrichments in 33S, and the oxidized species have depletions in 33S. The reduced species end up being bound up in sediments. The oxidized species ended up being bound up in the oceanic crust. If these were to be subducted, this package were to be subducted in the mantle and preserved, you should hope to then see it in hotspot lavas. James Farquhar, in fact, found that diamond inclusions, or sulfides hosted in diamonds, do have positive cap 33S anomalies, and he suggested that this is a result of a sedimentary component from the Archean being trapped in diamonds and then brought encapsulated, preserved, and brought to the surface in kimberlites. He suggested that altered oceanic crust would have the negative cap 33S anomaly, so we looked at the archetypal hotspot sampling that suggested to sample recycled oceanic crust. Rita spent 3 months going through kilograms of material and exposing individual olivine grains, and found only 2 sulfides that were large enough to get multiple sulfur isotope measurements. The measurements were made at the NORDSIM facility run by Martin Whitehouse. And here you go right here. We have cap 33S anomalies that are almost as negative in delta 33 space as Farquhar's diamond inclusions were positive. And James Farquhar and his student Michael Antonelli measured an olivine separate, and they found the olivine separate to have a smaller magnitude anomaly, nonetheless a resolvable anomaly, confirming the IM probe data. There are mass-independent sulfur isotope anomalies in these lavas. We now have additional data from a CPX separate, several whole rocks. The whole rocks don't preserve the mass-independent fractionation. This probably relates to 20 million years of alteration on a tropical island, so the sulfur has been replaced by secondary sulfur, modern sulfur. The clinopyroxene separates do have a mass-independent anomaly. This fundamentally changes our consideration of the chronology for the mantle. I think that we have always known that the subducted package went down well before yesterday, but now we know it definitely happened at this location before 2.5 billion years ago, that these ultra-oceanic crust was at the surface, resided for a known amount of time, at least 2.5 billion years in the mantle, and was brought back up again. So with that, I would encourage you to speak with Rita about her work, and thank you very much.
Thank you, Matt, for your 2 talks. Questions? Yes?
Matt, you know the question I'm going to ask you is, if you see this as a high news source, why is high news have such a low to 7 to 4? Why is it so flat?
So looking at the lead-lead space, the global array has been often interpreted as a 1.8 billion-year-old secondary isochron. And I think that that isochron has always been anchored by Mangaia. Well, Mangaia has to have a source older than 2.5 billion years, so I don't think we're dealing with two-stage lead here at all. I think it has to be 2 plus n-stage lead, in which case you can do pretty much anything. I was talking with Dave Graham last night over beer, and he pointed out that in the Hainen and Graham paper from '96, they noticed that the slope of the leads at Haimu Islands corresponded with an age of 2.7 billion years. So forget about the global array. Look at the lead isotope slopes produced by these individual ocean islands. And 2.7 GA, by the way, is very nicely bracketed by your age of 3 billion years for the initiation of deep subduction and the minimum age for the Haimu source of 2.5 billion years, which redefines for Mangaia lavas. So I think somewhere between 2.5 and 3 billion years is when this Haimu reservoir formed.
Francis?
Yeah, wouldn't you expect that if you can see a visible signal for cap delta 33, you would see some systematic deviation of delta 34 from the congruity value almost everywhere in the mantle?
I'm not sure why that would necessarily... I'm not sure we can do a mass balance with just a few samples from one hotspot. In fact, James Farquhar talks about a real issue of mass balance with CAP33S globally. After 12 years of data, there's a lot more data out there with positive CAP33S. There's a very small fraction of data with negative CAP33S. There isn't a mass balance yet just by looking at crustal reservoirs. I think the deep mantle might actually host much of the negative CAP33S anomaly. We just don't have enough data yet to do a mass balance model.
I think we should move ahead with 6 minutes late. The next talk, we're moving away from Hawaii, continuing in Mantle Plumes, is given by Karen Harp, invited talk on Galapagos and Easter, a tale of two hotspots.
Thanks very much, and thanks to the conveners for organizing the session. I'd like to take you to the Eastern Pacific for a little bit here. Where am I changing? Oh, right here. To maybe look at the Galapagos and Easter Island systems from a slightly different perspective than we have before. Al Hoffman and Aaron very courteously covered much of what I need to cover in the beginning of the talk, so we'll whip through this. So think of it as a review for the final exam or something. So Hawaii has obviously been very well characterized as a bilateral geochemical example of a bilaterally asymmetric plume in terms of geochemistry, with the more depleted Ka trend and the more enriched Loa trend. This has been attributed to deep mantle heterogeneity, according to models by Farnatani and coworkers. And of course, just last year, Dominique and coworkers proposed that this may be related to the location of the Hawaiian hotspot at the northern boundary of the large low shear velocity province. And they envisioned this kind of a model that we've seen already in Al's talk, where the more enriched material is sourced in the low velocity province and the more depleted material is sourced in the ambient lower mantle. And if we step back, very quickly, the chaos kind of began. And multiple hotspots have been identified with south side enrichment in the Pacific, and also, most recently, north side enrichment in the Society Islands, which is located at the southern boundary of the low velocity province. And so if we take a step back and we look at the Pacific basin in terms of where these hotspots are located, it looks like there's a growing source of evidence that we're seeing enriched material being derived from the low velocity province and the more depleted material in these bilaterally asymmetric hotspots coming from the more ambient lower mantle. And so we're sitting, the one exception to this might be Samoa. It's sitting near a subduction zone, and so I'm sorry, Matt Jackson, but we have to leave that for you to sort out on your upcoming cruise. But we're sitting in a really nice position here to look at this hypothesis a little bit further. The Galapagos Islands are located on an extension of the low-velocity province to the east on the north side of the boundary, and the eastern island system is located on the south side of this boundary. So that's what we're going to look at here today. So first we'll go to the Galapagos. They're located about 1,000 kilometers off the west coast of South America, and they're sitting on the Nazca Plate, not on the Pacific Plate, and the Nazca Plate is moving effectively straight east. They've kind of posed a bit of a challenge to those of us working in the Galapagos for a long time because we don't see nice linear arrays of geochemical variability in the Galapagos like we do in Hawaii. Instead, we see what we call the Galapagos horseshoe. And the horseshoe is referring to the distribution of more enriched signatures in the archipelago. They're concentrated on the western and southern peripheries, and lavas get progressively more depleted as you move towards the east across the archipelago. Numerous models have been proposed to explain this pattern, but they fall into two big categories. One category has the depleted material being sourced in the upper mantle, being entrained into the plume through some kind of deformation or thermal mechanism. And the second model has the depleted material being an integral part of the plume itself, perhaps even originating in the deep mantle as was proposed by Kai in 2000. But we hadn't really looked at the Galapagos through the lens of the bilateral asymmetry model. And so if we release ourselves from the shackles of the horseshoe, I think we can actually make a decent case that there may be bilateral geochemical asymmetry in the Galapagos. You can divide the lavas into two big categories on the basis of their isotopic characteristics in basically any isotope system you look at least so far. And in general, those more enriched materials are found in the south, and the more depleted materials are found in the north. It's a little more clear when you look at it in map view. And the critical difference here is that the chemical boundary between the more enriched and the more depleted regions doesn't run parallel to plate motion. It runs oblique to plate motion. So you can see it here shown as the yellow line. If we zoom back out and we look at this in the context of the map of the low velocity zone, you can see the Galapagos located here in the northeast. And interestingly, that northwest to southeast chemical boundary that we just mapped in the Galapagos corresponds pretty closely, at least to this particular model, of the low velocity zone. So it looks like we have a different orientation, as was mentioned by someone who asked the question of Al's talk earlier today. So we may be seeing some kind of relationship that's a little more concrete between the low velocity zone and the distribution of chemical heterogeneities. So this brings us to the question of Easter Island. Easter sits on the southern boundary of the low velocity zone and gives us an ideal opportunity to test this hypothesis a little bit further. We would predict, logically, that we should see some kind of north side enrichment, the mirror image of what we see in the Galapagos down here at Easter. Easter sits just off the east coast of the EPR. It does, in fact, also sit on the Nazca Plate, southern end of the Nazca Plate, and it does define two clear volcanic chains. And if you look at the isotopic distribution of lavas that have been collected from Easter, even though the two volcanic chains overlap in space, they do seem to define two well-delineated, distinct isotopic compositions. We see also north side enrichment here, the mirror image of what we see in the Galapagos, with more enriched signatures in the north and more depleted signatures in the south. Same plots shown here for the isotopes that I showed you for Galapagos, and you can see it's effectively the same pattern. The only difference is that we flipped where the enriched material is in the north versus the south. So to compare the two against each other, Galapagos versus Easter, basically the identical distribution or very close to the identical distribution of isotopic ratios, but with the mirror image relationship between the location of the southern or location of the depleted material versus the enriched material. So we refer to these sometimes as the Tweedledee and Tweedledum of hotspots because of their mirror image location, right? Remember, you're old. Never mind. Okay, so, and again, extending Dominique's model a little bit further, we think we're seeing some kind of an expression of the low velocity province supplying the north side of Easter and the south side of the Galapagos system. So what are the implications of this set of observations? Well, perhaps it's as simple as finding two more hotspots that we can add to the pantheon of bilaterally asymmetric hotspots. I'd like to say they're the first two discovered or observed off the Pacific plate, but that's not true. If you've already heard in Al's talk, there's a paper coming out in geology by Kai's group in the Atlantic, and we're going to hear more in the rest of the session as well. But I think there are some important implications that reach beyond that. Like I said, it does expand this hypothesis. It gives more data that may support it, and it's certainly something we need to investigate in the future. More importantly, perhaps, at this stage, is that both the Galapagos and Easter Islands are near ridge hotspots. Both of them, there's very well documented evidence in both cases, particularly the Galapagos, that the plume affects the ridge and that the ridge affects the plume. Despite this plume-ridge interaction, we still see some preservation of bilateral geochemical asymmetry in these systems. So that means that the source of the heterogeneity supplying both Easter and the Galapagos must be deeper than the shallow plumbing systems that govern plume-ridge interaction and the way mid-ocean ridges work. So I think that's a very important thing that we can draw from this particular story. And of course it leads to where the excitement is in this story, and that's that maybe if we start looking at some of these hotspot systems in a little more detail and carefully, we might be able to start to map the geometry of the geochemical heterogeneity in the lower mantle. And that's, of course, where, like I said, the excitement's emerging. There are two more comments I'd like to make quickly before I close that are maybe caveats about ways to think about what we're looking at with these asymmetric hotspots before we jump too much on the bandwagon. The first is I think we need to consider the geometric relationship between the geochemical boundary and plate motion. So at Easter in Hawaii, in the Marquesas and the Societies, for instance, plate motion appears to be parallel to the geochemical boundary. And as a result, you see nice, relatively clean stripes of different geochemical compositions parallel to plate motion, kind of like you took a tube of Aquafresh toothpaste and smeared it along a table. The blue stripe would stay the blue stripe, the red stripe would stay the red stripe. But if you go to the Galapagos, the geochemical boundary is oblique to the direction of plate motion, and this is just what Al was referring to, I believe, in the second part of his talk. And I think this has some implications for what we can actually see on the surface if we are looking in detail at these hotspot systems. It's well established in the Galapagos that volcanoes are active for oftentimes up to 2 million years, well past where they originate in terms of plate motion, so they're carried off what we might call the plume stem in conventional language. So if you imagine a hotspot or a volcano that's formed and supplied by the enriched component of the plume, it'll continue to erupt as it gets carried away from that location in the direction of plate motion, and eventually will cross that chemical boundary and start to be supplied, while still active, by more depleted material. That means that the more depleted material is going to overlie stratigraphically the more enriched material, and conceivably in a way that we can't see when we just collect samples from the surface. So I think that's something we really need to be aware of. We know of at least one example in the Galapagos where the more enriched material underlies the more depleted material. That's Santa Cruz volcano, which is basically under the blue circle. And I'd urge you to go see Emily Wilson's talk poster tomorrow in the poster session that's reporting new fieldwork from Santa Cruz that shows just this point. So this may be something that we really need to keep in mind when we're looking at these hotspots on a global scale. And the second issue that I'd like to mention is that the southern component, or the more enriched component that may have as its source the low velocity zone, shares a number of specific geochemical characteristics. The first is that all of the more primordial or high helium 3-4 signals that we find in the Galapagos, they're all located in the southwestern part of the Galapagos. We don't see anything with an elevated 3-4 signal in the northeast at all. Second, those high helium signals are generally accompanied by a high Titan signal. And what I mean by that is that is elevated concentrations of the high field strength elements, niobium, titanium, tantalum, and that's been associated with high helium 3-4 signals by some of Matt Jackson's work in the past as well. It's like homage to Matt Jackson. And the last is that there is very strong evidence for variable but ubiquitous contributions from recycled ocean crust, very much along the lines of what Aaron was just talking about. And I think we need to take very seriously a lot of what Aaron's been proposing in terms of this contribution of recycled ocean crust to these signals in the mantle plume systems. And it's possible that if this whole system, this whole hypothesis that Dominique has proposed about the low velocity zone sourcing the enriched material in some of these asymmetric hotspots, we may be able to get actually a pretty good grip on the nature of the chemical compositions of these lower mantle reservoirs, and that the truth really lies somewhere in between the two extremes to hypotheses out here, Aaron's about recycled material and the asymmetry from the deep mantle. It's probably a combination of the two. So with that, I would like to thank you for your attention.
Thank you, Karen. Are there any questions for Karen? Al.
I think, you touched on the $64,000 question, namely, how do you associate the high helium-3 with strong evidence for recycling? And so I think this drives the story back to where the helium has to be either entrained or diffused from a separate reservoir into the source, which itself is recycled.
Right.
And I think that is the only simple way that I can think of to resolve this.
Yeah, no, I do agree with you. And I think if we look in detail, at least in the Galapagos in this case, we can see some evidence for that. I'm pretty sure that we're seeing variable amounts of recycled material contributing to that southern component, and you can track the helium as a direct relationship to that. So, thank you.
Thank you, Karen. So we're going to move on to the next talk. Newly minted doctor, Dr. Schroedel, is going to tell us about the Plume double chain in Iceland and how this chain can be explained. Take it away.
Thank you. So what I'm going to do today is present some observations from Iceland, some new isotope data we've got in Iceland, combined with literature data to explore the geochemical spatial structure we can see in the Iceland hotspot, and see what comment that may have on, how that may be able to comment on the isotopic double chains we've been seeing about this morning. So this is a figure which has come up repeatedly, and what I really want to do is start with this, because I guess I'll come around and comment on it in the end. And I suppose what's been done here is spatial structure that's been observed at the surface of the Earth, measured in the isotopic composition of basalts, has been mapped from the surface and extrapolated down into the deep mantle. And so, as has already been said, this is potentially an incredibly powerful tool in which mantle plumes are actually telling us about structure at the very base of the mantle. But one of the difficulties of doing this mapping and getting the spatial structure in places like Hawaii is that there's very limited spatial resolution offered by the volcanoes actually producing the samples, because it's a parallel chain, so you've got only really two dominant volcanic edifices sampling the mantle. So somewhere which offers a bit greater spatial resolution is Iceland. So this is Iceland here, situated in the North Atlantic, and because in this case the Iceland plume is juxtaposed with the mid-Atlantic ridge, you get distributed volcanism across the island, and that gives you sort of more continuous spatial sampling of the mantle. And so this figure here is a close-up of Iceland, and so the mid-Atlantic ridge is coming in on the southwest here in the western volcanic zone, stepping across to the eastern volcanic zone in central Iceland, and then leaving Iceland in the north. And so these colors are how I'm going to color the data points to begin with, and these are Iceland's neovolcanic zones. And we've contributed new data to this Dingjafoot area in central Iceland, new samples measured by MCICPMS for lead, neodymium isotopes, strontium isotopes, majors and trace elements. So the questions we want to ask are, is there geochemical spatial structure on Iceland where we've got this more distributed volcanism? Can we see similar patterns to have been observed on other ocean islands? And we're going to do this by analyzing the data grouped in isotope space, and I suppose that's the sort of analysis method we've been seeing this morning. And then the second stage is going to be to sort of discard that grouping of data and analyze the data purely according to its spatial information, so literally the latitude and longitude location of the samples, to try and recover a bit more information about the spatial structure. So this is the data in lead 28204 against epsilon neodymium, colored by geographic location, so blue in the southwest, red in the north, and then our new these are our new data from central Iceland, just there in green. And you can see they fall intermediate compositions, in lead isotope space at least. Adding in sort of literature data now from this broad eastern central Iceland region, you can see they fall in a similar location. So now what we want to do is statistically test whether or not these offsets in data populations, whether they're meaningfully different from one another. And to begin with, we're going to do that by looking at the mean isotopic compositions. So what I've done here is just collapse the data onto the y-axis and x-axis respectively, and plotted what are effectively histograms of the data. So you can see here on the x-axis is for epsilon neodymium, the histograms for central Iceland in green, south in blue, and north Iceland in red, they all sort of effectively overlap one another. Whilst in lead isotope space, lead 2824, you can see that there are systematic offsets where North Iceland is less radiogenic than Central Iceland, which is less radiogenic than South Iceland. And these populations can be tested statistically for differences using the Kolmogorov-Smirnov test, and these are p-values returned, which the smaller the p-value, the more dissimilar the distributions are. And you can see for neodymium isotopes, you get p-values of 4%, 0.1%, whilst for lead isotopes, the p-values are much less than 0.01. So what we're seeing here is a difference in the lead isotopes, which isn't reflected in neodymium isotopes. Another way we might want to look at the geochemical data is in terms of its mixing array, and so these are binary mixing curves plotted for the data. We can do the same statistical testing, and what you see is that using an F-test this time, is that the binary mixing arrays, this time Central Iceland compared to North and South Iceland, the binary mixing arrays are again statistically different from one another. And those thinner lines are showing what the effect of systematically removing data from particular labs one by one to see if there's any sort of lab bias effect, and that's not important here either. So what we've seen by looking at Iceland's geochemical data in isotope space is that there are progressive shifts in not only the mean isotopic composition as you move across Iceland, but also in the binary mixing array the data defines. But by grouping the data by volcanic zone, we've sort of discarded some of the spatial information. Well, we've discarded its latitude, longitude location of where the sample's been erupted. And that potentially contains a lot of useful information about actually the length scales over which the mantle's varying. So what would be great is if we could analyze the data purely in the spatial domain, combining the geochemical information, and see if we get any extra information out. So these are maps of the raw geochemical data now. On the left, the neodymium isotopic composition, and the samples are colored by neodymium isotopic composition. And on the right, colored by lead isotopic composition. And you can see previously, well, we didn't see much spatial structure in neodymium isotopes, and that's maybe reflected here by the fact that there doesn't appear to be any systematic trends as you move around Iceland in neodymium isotopic composition. There's a lot of variability locally. For lead isotopes, you can see that there are hints of spatial structure here, where in North Iceland, lead isotopes are more depleted than in South Iceland. It's intermediate in Central Iceland. But at the same time, there is a lot of local variability, which is perhaps masked in those original analyses, the original analysis. So what we want to do is ask the question, is the compositional distribution of samples spatially non-random? And what is the decoupling length scale between lead and neodymium and strontium isotopes? Because lead is clearly behaving a little bit differently here to neodymium isotopes and strontium. And so the way we're going to do this is by constructing this plot of cumulative geochemical variation against sample pairing distance. So what we've done here is taken all the samples in the data set, so it's over 100 here, and paired every sample with every other. And for each of those pairings, you get a sample-sample separation distance. And for that separation distance, you can calculate a geochemical misfit. And so if there were long-range spatial structure to the data set, you'd expect samples with large sample pairing distances to have a large geochemical misfit, and samples with small pairing distances to be more geochemically similar and therefore have less geochemical misfit. And so what this plots is the cumulative variation as sample pairing distance is increased. And these grey profiles here are the synthetic profiles for a random spatial distribution, a random spatial geochemical distribution. So what I'm going to do now is plot on the real spatial geochemical distribution for lead, neodymium, strontium isotopes and see how they compare to this synthetic random spatial distribution. So in blue and red are the strontium and neodymium isotopes, and you can see they overlie quite closely. the pattern you get for a random spatial distribution of isotopic compositions, whilst lead isotopes are significantly offset from this, and they're offset to a lower cumulative variation for a given sample pairing distance. And what this is saying is that the lead isotopes accumulate most of their geochemical difference at long or large sample pairing distances, so that there's large-scale geochemical structure in lead isotopes in Iceland that isn't present in strontium and neodymium isotopes. And we can, again, statistically test this, and this plot's recording the Z-score, so a misfit basically between the synthetic grey profiles and each of the real profiles, and the higher the Z-score this time, the more different they are. This grey region is the 95% confidence region, and you can see only the lead isotopes lie significantly outside that, and the spatial structure in the lead isotopes really picks up after 100 kilometers sample pairing distance. So the conclusions from Iceland then are that we can see a spatial structure in the lead isotopic composition of basalts that we can't see in neodymium or strontium isotopes. That spatial structure is there both in mean composition and in the binary mixing array that the data defines. These spatial shifts are progressive, and that the decoupling length scale between lead and the other isotope systems is around 100 kilometers. So now we want to ask is kind of how does Iceland comment upon the double chain story that we've been hearing about this morning? And so what these cartoons here are showing are sort of maps of the chemical structure in sort of fictive plume conduits. And on the left, you've got sort of the bilateral asymmetry, blue and red. In the middle, you've got a gradational change, blue to red. On the right, you've got a more or less arbitrary chemical distribution, and the colors are reflecting then the chemistry or some chemical parameter. And I suppose in Iceland, from what we've seen, the temptation is to put Iceland in this sort of central scenario here, where by virtue of having distributed volcanism, we've been able to resolve a progressive shift in the mantle's composition south to north, which maybe is not possible to see in places like in typical ocean islands, where you've got a parallel chain. So you don't get that resolution in the middle, basically. But the caution I'd add to this is that what we don't really know is the mantle volume that's being sampled by any given eruption. And so that's really the key thing for mapping the spatial structure of geochemistry at the surface of the Earth in basalt into the mantle. And without that information, that exercise of mapping from the surface to the deep mantle, or even the shallow mantle, in fact, is difficult. And specifically with regard to double chain volcanism, there's the danger if you only have two sampling locations effectively, so one of two volcanoes in the double chain, that almost irrespective of the spatial structure, you're going to end up with an apparently dichotomous compositional relationship between those volcanoes. So the issue is that poor spatial resolution at ocean island chains, and in fact at Iceland as well, it's not absolved from this difficulty, means that mantle chemical structure is not easily, if not uniquely, determined in these settings. So I'll leave it at that. Thank you.
Thank you, Oliver. I'm sure there are questions. In the back there.
Thanks. It seemed like most of your lead isotope variation was dominated by the ridges as they came on land in Iceland. Can you comment on how much of that variability is potentially due to the structure of the ridges themselves, or the structure of the sources of the ridges are having, as opposed to the spikes that you're actually sampling in Iceland?
Yeah, so if I can flip back, maybe I can do that very quickly. So the comment was on the variability that's being seen, specifically that there's greater variability at the margins here than in the center. And so what you can sort of see that reflected here in the shape of these distributions of mean lead isotopic composition, where the central Iceland one is much narrower than the lead isotopic distribution in either South Iceland or North Iceland. And so that's something we have looked at. And in fact, a primary cause for these differences in the isotopic variability is simply to do with the evolution of the magma and the thickness of the crust. So if you incorporate the Mg number into this analysis, you see a lot of the geochemical variability is simply being controlled by the evolution of the magma. The more evolved magmas have mixed together more, and a lot of that initial variability has been homogenized out. But there is a real signal that remains, even accounting for Mg number, in terms of variability, and we don't have an explanation for that, in fact.
Francis, a quick question.
Yeah, sorry for being so geeky, but why did you
Yeah, so we do also look at, so this is, the question was, why did we only look at a one-dimensional statistic for describing the spatial structure rather than multi-dimensionalizing that statistical analysis? The simple answer is that the one-dimensional statistic was simpler to describe in 12 minutes. There's a long paper that's been written behind this, which 60 pages of statistics, and I'll send it to you so you get your fill.
Thank you, Oliver. We're going to move on to the next talk. Connie Class is going to tell us about the role the LLSVP plays in spatial and temporal variability in plume source regions in the South Atlantic. Thank you, Connie.
Okay, I want to change areas now and move you to a less familiar area that has been much less studied than the Hawaii, Iceland, and Yellowstone plumes we heard so much about in this meeting. I want to talk about the South Atlantic, where we have 4 very closely spaced hotspot trails, the Tristan Gulf Hotspot Trail, Discovery, the zigzag, little awkward trail of the Shona, and Bouvet. I've been discussing that since a while. I just want to hint at that. For the geochemical variability, a lot of scientists have pulled to shallow continental sources from the recent breakup of Gondwana. I don't want to discuss this again here. This is all published work. What I want to focus on are deep sources. So if we want to talk about deep sources for this area, we first have to justify that we actually do look at mantle plumes that come from the lower mantle. Few will question that for the Tristan Gulf plume, which is a major feature in the South Atlantic, has formed one of the biggest flood basalt provinces. It has age-progressive volcanism since 130 million years. So it has been categorized as a type 1 plume by Courtillon in 2003, supposedly coming from the lower mantle. However, I want to add a word of caution. It is not a high helium plume like the other major type 1 plumes. And in addition, if we look at the younger half of the Volvis Ridge, we're looking at diffuse volcanism over a wide area that has not been observed for the other type 1 plumes. And just as a quick outlook, we actually have been able this year to go on a cruise and sample this younger end of the Volvis Ridge. I mean, you hardly recognize it as a single plume track here. So hopefully you will hear more about that in the following years. This work is also complemented by a German cruise that will add on to the old end of the Volvis Ridge. Now, the other plumes in the South Atlantic lack flood basalt provinces that would allow to constrain the lower mantle source for them. However, recent work just published by John O'Connor and co-workers identified the Shona plume as a long-lived plume system for at least over 80 million years. That awkward zigzag shape that is implied for this plume track comes due to the now extinct Agulhas ridge, and you had a ridge jump then to the now present position of the South Atlantic ridge. That's why you have this awkward plume track. The Discovery plume is now identified to be active over 40 million years. However, that on its own is not sufficient evidence for a lower mantle source. And still our best, most compelling evidence for a lower mantle source is helium isotope data. This is already has been shown by Sarda in 2000. Basically, if we have helium isotope ratios that are elevated relative to normal MORB, we assume a lower mantle origin. And for South Atlantic ridge data, it has been shown that the Discovery plume goes up to 15 RA and the Shona plume up to 12 RA. And also Kurtz showed that Bouvet plume has elevated helium isotope ratios. So if you take the evidence together from the presence of a flood basalt province for the one, the longevity for two of the plume sources, and plumes, hotspots, and the high helium isotope ratios for three of them, I think we have good evidence that we look at lower mantle sources. Now, when we've seen this diagram, the global tomography model identifies the African and Pacific LLSVP regions, and the red line that you see is the 1% contour of the S-mean model by Becker and Boschi from 2002. Torsvik and co-workers have identified that based on reconstructions of flood basalt provinces and also for some active plumes, that they come to lie, most of them, almost all of them, come to lie close to this edge of the LLSVP regions. Now, it's very striking if we look at the position of the 4 South Atlantic plumes, how they line up like pearls on a string along this edge of the African LLSVP. This becomes even more visible when we zoom in, and here you see the 4 South Atlantic plumes. Again, this is the 1% contour line at 2,800 kilometer depths near the core mantle boundary that I showed that was shown in the previous diagram. And what we find is they lie very close to the edge, with maybe the exception Bouvet is a little off. And we have synchronous volcanism along all these plume tracks. That again is shown in a figure of John O'Connor. I should point out that actually John O'Connor has a poster on Friday as part of the same session with some shallow and deep aspects for plume. Please come visit the poster or look at the paper. So we have synchronous volcanism, at least for 40 million years, for 3 of the plume systems, and for 80 million years for Tristan Gulf versus Shona plumes, which further supports that they have a lower mantle origin, obviously now coming from the edge of the LLSVP. We heard so much now about zone plumes. I don't need to show the same diagrams that have been shown in previous talks. The Tristan Gulf plume turns out to be the first zone plume identified in the Atlantic and related to the African LLSVP. This is work that is in press now in geology by Rode from Kai Hörnler's group and co-workers. And what it shows that in 2007, 2004 lead, 2006, 2004 lead, you have 2 populations with a so-called Tristan track in blue, which is shown here, versus the Gulf track in yellow at elevated 2007, 2004 lead isotope ratios in yellow. And what is special about this is 2 things. One is it's active for up to 70 million years. And second, that the north-south separation is at 90 degrees to the edge of the African LLSVP. Zone plumes are everywhere. The data are very sparse in that area. For the little data that we have, it looks like that the discovery plume might also be a zone plume. We have a northern component, which is kind of a Gulf-type composition shown in red, which is sampled along the South Atlantic Ridge and some of the seamounts. And we have a southern component with more of an EM1 type composition shown in blue, again sampled over 40 million years on the seamount and on the present-day South Atlantic Ridge. There is maybe some more complexity because the white symbol is kind of arguably an intermediate composition that also is found in the south. And I want to mention the Shona plume. There's simply insufficient sampling at this point to allow to identify zoned versus non-zoned plume. Now, what is important, what I want to point out, and what further constrains the lower mantle source of all these plume systems is when we look in 2007, 2004, 2006, 2004, the GUF component, which is the signature that was first identified in GUF Island, and then now in the zone plume paper that I showed extends all the way up to 70 million years. I haven't plotted that yet because the data are not published yet. But I show here up to 19 million years, that signature. We do find the same signature also in 2 other of the 4 plume systems. We find it in Discovery, in the Discovery seamounts, and Morp, South Atlantic Morp affected by the Discovery plume. And we also do find it at 40 million years and 80 million years along the Shona plume track. So this is shown here in the context of all the other components of the South Atlantic plumes. And this shared component in 3 of these plume systems further supports that they actually do have a shared lower mantle source now at the edge of the LLSVP. This yellow line is again the 1% S-mean contour. Now the southern hemisphere plumes are characterized by the so-called Dupas signature, which is visible in 208, 204 versus 206, 204, with an offset to higher 208, 204 relative to, for example, North Atlantic Morp. What we find is that basically almost everything from the South Atlantic plume systems that I show here have this Dupas signature. And this Dupas signature also does not distinguish between the northern Tristan track versus the southern Gulf track along the Tristan Gulf plume track. So this signature can be related to the LLSVP. Here again we see the contour. Now you have to keep in mind this contour is for present day. The work by Torsvik has shown nicely that the location of flood basalt provinces indicates that this edge probably was rather stable over hundreds of million years, possibly. So basically, given the synchronous volcanism along these plume trails, you have to imagine that back through time, all these samples are coming from the same edge of the African LLSVP. Interestingly, we find also a few non-Dupas compositions. These are mostly on the southern end of the area. We have the young Shona and we have the Bouvet. They have non-Dupas signatures. So maybe these are the only exceptions. They're the furthest distance from this identified edge of the LLSVP. Maybe these are sources not related. However, we have very rare but additional samples at older stages that are not Dupas, so maybe there's additional complexity. So what I have produced for you, I have discussed the lower mantle origin of these plumes. I have discussed the compositional variability. So what we can do is we can do a map of what actually this edge of the LLSVP looks like over the last 80 to 130 million years. I distinguish the 3 major components, the Tristan, the Gulf component, as I discussed, and the presence of the EM1 composition. And this map, of course, is just on the surface, back through time. What we really want to know is what does it look down there at the edge of the LLSVP. But as Elle showed, there is an additional complexity. The work by with Cinzia and Al shows we can sample areas far away from the actual position of the plume. So a direct translation to the base of the mantle is not possible. What we need is we still need to have a dynamic model that ties these compositions that we observe on the surface down. And this is obviously different if you have 1 plume or if you have 4 closely spaced plumes coming from an edge. So this will be continued. And here are my conclusions. Thank you.
Connie, thank you very much for this talk. Please, are there questions for Connie? Can you speak up, please?
I did not understand everything, but basically you say it's difficult to distinguish deep versus shallow signals. Is that the major question? Well, I couldn't go into detail. This is not correct. Most of these seamount trails in the South Atlantic are further away from the mid-Atlantic ridge when they formed. Difficulty, of course, is that we're looking mostly at old seamount samples that form these trails. But we can distinguish, if we go in details in the isotope data, we can clearly distinguish areas that are close to the mid-Atlantic ridge where we see mixing towards mob-type compositions versus locations where this is not the case. So I don't think the major compositional variability is impacted by that.
Please, one very quick question there. Can you speak up, please?
Okay, so it was commented that these contours are probably not should be taken with a grain of salt, but in this case it fits amazingly well. I mean, the South Atlantic plumes align in a way that suggests there is real significance with the edge of the African LLSVP.
Thank you very much, Connie. We're going to move on to our next talk. Catherine Chevelle is going to tell us about isotopic diversity and how it relates to plume strength. Because we're behind, Catherine's going to tell us everything in 5 minutes.
I
Just
try.
kidding, Catherine.
I will try.
Thank you.
Okay, thanks very much. Thanks for actually a very interesting session altogether. Today I'm going to talk about isotopic diversity, and I'm not going to talk about isotopic stripes, or very shortly at the end of the talk. And what I want to focus on is, what I want to focus on here is basically the isotopic heterogeneities as sampled by various plume chains. So here is just a sketch of, a compilation that I did recently of about 10,000 samples in the GeoRock database, and this is just to show that worldwide, all oceanic island basalts define a very large range of isotopic composition, here neodymium and here strontium, with these extreme Samoan samples. So what I want to do today is answer two kind of simple questions, is try to tackle down the size of the isotopic heterogeneities in the mantle. And I want to also address the question of how much melting homogenizes the source diversity that was there to start with. So to do this, I'm going to relate the isotopic diversity sampled by plumes, individual plumes, to the magma production rate. So let's first maybe see how, I'm going to basically address the question using the data coming from 4 major locations: Hawaii, the Canary Islands, Reunion Islands here in the Indian Ocean, and the 4 chains in Polynesia. So magma production rate, so what is it exactly? What I'm going to calculate is basically a volume of erupted lava per unit of time. So to do this, in some cases, like in Hawaii for Big Island, for Reunion Island and for the Canaries, I used the published data that provided the volume of erupted lava for each of these locations. For other places, and in particular for Polynesia, we use the bathymetry on the seafloor to determine the volume of the seamounts and the emerged islands, and on top of the bathymetry we added the volume of emerged surfaces, which represent very little, usually less than 5%. So this is how we calculated the volume, and we also needed to know the duration of volcanic activity, and for that we had to use well-dated ages and samples, so we know how long the volcanic activity has been going on for. So now the isotopic amplitude. So here is the first example of what we did for Hawaii. And what we did, in fact, unfortunately, I mean, some of you might have heard the talk by Mike Garcia. The older part of the chain is very poorly known, so we couldn't do an estimate using the entire chain. So we concentrated on data only from Big Island at the active end of the active end of the chain. So what we see there is that basically roughly 200,000 cubic kilometers of lava have been produced in 1 million years in Big Island. So now when we look at the isotopic range that exists in Big Island, you can see here in pale gray the range known for all OIBs, and there's supposed to be a pale yellow field that you don't see, but it corresponds to the arrow here. This is basically the range known for all OIBs worldwide in terms of neodymium isotopic composition. Here, dark gray is the field known for Hawaii, and we see that Hawaii represents roughly 20% of the total range. If I use another isotopic system here, lead-lead isotope, you see that similarly Big Island represents roughly 15% of the total range. So now I move to another case, which I call the weak plume case, and I will show you data and calculation for the 4 main island chains shown here on the bathymetry map. The Austral Cook Island chain here, that you can barely see behind the white arrow. The Society chain, this is a very small thing here, that lasted for 4.5 million years. The Marquesas chain that you already heard a bit about today, here, and the Pitcairn chain here below the white arrow that you can barely see either, that lasted 12 million years. We have no data for any of this big thing, which is called the Tuamotu archipelago, because there is basically only atolls and no drilling that has been done. So if I take Polynesia as a whole and do the same evaluation, so here is the various colors showing the 4 different individual chains, Austral Cook, Pitcairn, Gambier, Marquesas, and Society. And you see that if you take the lead isotopic system, in terms of 206 over 204, Polynesia covers basically 100% of the known variation worldwide. So it covers a very large range. In terms of neodymium isotopic composition, it's 80% of the known range. And all of that for a total magma production that is roughly similar to what I showed before for Hawaii, but here this time it's over a period of 20 million years. So here we have a very much lower magma production per million year, about 7,000 cubic kilometers. So now I can go quickly through the various Polynesian individual chains. The Austral Cook here, with a total volume that is still more than 100,000 cubic kilometers, but on average a production rate of only 6.6 thousand cubic kilometers, and 80% of the lead isotopic variation known worldwide. So we see that, for example, in this case, in the Austral Cook, which is very famous for the extreme high mu composition, not only we have the extreme composition, but we have the whole range. So large diversity. Similarly, in the Pitcairn chain, where the magma production is about only 3,000 cubic kilometers per million year, we observe a very large range in terms of neodymium isotopic composition, covering 80% of the known worldwide range. So we see the picture emerging. The lower the magma production rate is, the larger the isotopic diversity is. And last example in Polynesia, first of all, the society chain here with a relatively high, by Polynesian standards, magma production rate. And we see that in lead isotopes, society covers 15%, so much lower proportion of the total. And in neodymium, 45% of the range, which is also much lower than what I showed in the previous slide. And so now if we focus on only Tahiti within the society chain, this is what I have in this slide, we see that the magma production is basically double of what was known for the society. And in that case, you see that both for lead isotopic composition and for neodymium isotopic composition, the range is smaller than it was for the society. So quickly, I show you the data for two other places, Canary Islands with a relatively low magma production rate at about 10,000 cubic kilometer, 30% of the isotopic range. Reunion Island, where the magma production is much higher, 20,000 cubic kilometer per million year, we see that the isotopic variability is much lower than it is in the Canary Island. So same picture again. So here is a plot that just shows the summary of what I showed you. In the top panel, for each island chain, I plotted the variability of the 6 different isotopic ratios: neodymium, strontium, hafnium, lead, 206, 7, and 8. And what the general picture is on the x-axis is plotted the erupted volume of magma per unit of time. So what the picture is that basically the lower the magma production rate is, the larger the isotopic variability is. The most variable isotopic composition being not always the same. Pitcairn, it's neodymium, and Austral Cook and Canaries, it's the lead isotopic composition. We can make an average of all of those, and we see that the picture is still remain the same. Low erupted volume, higher variability. That, I think, fits quite well with what is known from the trace elements. Here I just quickly plotted a figure that published by Al Hoffman in the Treatise of Geochemistry, where you can quickly compare the trace element pattern of Hawaiian lava, shown here in purple, with the typical composition of basically what are lavas from Polynesia, the Mangaya, the Pitcairn, and Tahaha, which is one of the Society Island. And you see that in those 3 cases, the enrichment in very compatible elements are much higher than in Hawaii, suggesting smaller degree of melting in this weak plume than in the strong plume, such as Hawaii. So now the scale of the heterogeneity. That's another exercise that we did because we had the great advantage of having extremely well-dated lavas in the Marquesas Islands in northern Polynesia. So here, I just, this is a general range of the isotopic composition that we measured for neodymium and strontium in the Marquesas Island. And you can see there are 4 high islands that I highlighted: Huauka, Motane, Tauata, and Fatuiva. The duration of volcanic activity in each of them is given here in this pile. What is important is to compare the light-colored dots to the dark-colored dots. The dark-colored dots shows samples whose age is less than 50,000 years apart. Okay? And we see that in the 3 islands where we have such data, we see that significant different isotopic composition occur within less than 50,000 years. This is the case also here. It doesn't show much because of the scale down there, but it's very significantly different. And also the case for Tauata here with the 2 dark orange spots. So using these differences, we know that the source was different. We know it happened in less than 50,000 years. We know from the magma production rate that 400 cubic kilometers of lavas could be produced in that amount of time on average. And we know that the basalts are basically basonite and alkali basalt, so low degree partial melting. So we can calculate the size of the sphere, of the source that produce lavas with different isotopic composition. And when we make this calculation, we reach roughly 8,000 cubic kilometers for the source volume, which corresponds to roughly a 10-kilometer radius sphere in the mantle. So it is very small. So now just a few words before I conclude about the isotopic stripes that have been mentioned ever since this morning. So just to relate that to what I showed you about the size of isotopic diversity versus plume strengths, I think that in the case of Hawaii, we have the case of a strong plume. Here is a picture that everybody has been showing ever since this morning of Dominique. And here I think we have a clear case of very different materials coming from far down through a very strong and plume that produce a lot of lavas. I think, and this corresponds here to the deep plume from Cortillo. When we look at weak plumes, I think the picture is a bit different. I think that the diversity is at very small scale. It's actually different in nature. Here we're talking about neodymium and strontium. We're not talking about lead differences as the case in Hawaii. We also have big variability in the austral, in the Pitcairn, and in the society. And I think that in this case, as a weak case, we are more like in the plume, the second category of plume suggested by Cortillo, with a very heterogeneous material located at the top of the lower mantle and several little conduits bringing things to the surface. So just my conclusion. In conclusion, strong plumes are isotopically more homogeneous than weak plumes. Partial melting homogenize the sources heterogeneities. I think I convinced you that we can show that different isotopically distinct mantle source can be very small, and here I evaluate it to be less than 10 cubic kilometer sphere under Marquises. And as a final conclusion, I suggest that strong plumes provide average composition of source material, while weak plume trace isotopic diversity, and the two should not be mixed up. Thank you.
Thank you, Catherine. I'm sure there are questions for Catherine.
No, they all want to have a coffee.
Al.
I think you can see similar phenomenon on mid-ocean ridges.
Yeah.
When you go to the East Pacific rise,
yeah.
The compositions look very homogeneous, and there are presumably big magma chambers which mix things up. You go to the Atlantic, those dwelling places, and then the variability increases.
Yeah.
And so these large degrees of melting simply hide the...
Absolutely. Absolutely, yeah. Yeah.
Esteban, you have a question?
I'm sorry, I didn't hear the beginning of the question.
If you think that there's a lithospheric component in the heterogeneity we're seeing outside of Hawaii,
I don't think so. I think it's in the plume, but it's just very small scale. It's a real marble cake. I mean, it's small scales, and it's sampled at small scale because the plume is very weak. So you get the diversity present in the source. I'm not saying it comes from the lithosphere at all. Okay?
Okay, plumes, what do we really know? Join us after lunch until 6 p.m. We have a couple more sessions this afternoon. And posters tomorrow.